Good morning, everyone. Welcome to the second day of ICCP. Welcome to the morning session. Today's session is going to have 4 exciting papers. And we are going to go through each of the papers like yesterday, the same way. We are going to play the video. Then we have question answer session and moving on to the next paper. So my name is Vivek Bhuminathan. And today's paper, all the 4 papers are going to talk about taking some kind of low resolution information, either in space or time or quantization, and produce high resolution output. And also to note, the 4th paper in the session is also the best paper award winner at ICCP. I request everyone to ask questions on the live chat, and I will pull questions at the end of the video to ask the authors. Without any further ado, I'm going to introduce the first paper. The first paper is Deep Slow Motion Video Reconstruction with Hybrid Imaging System. And the authors are Avinash Paliwal and Nima Kademi Kalanantari. The presenter today is going to be Avinash. Please take it away, Avinash. And also, one more thing, this paper was also accepted to the PAMI special issue. Please take it away.
Hello, I'm Avinash Paliwal, a first-year PhD student at Texas A&M University, and I'll be presenting our work on reconstructing slow-motion videos using hybrid imaging systems. Slow-motion videos are becoming increasingly popular and is a core feature of most of the digital and smartphone cameras today. The camera hardware, however, has a limited bandwidth and therefore can either capture high-resolution videos with low frame rate or low-resolution videos with high frame rate. For example, the Nokia 6.1 is capable of capturing 1080p videos at 30 fps, but can only capture videos with 120 fps at a low resolution of 480p. Therefore, capturing high-resolution, high-frame-rate videos using standard cameras is challenging. A large number of techniques generate high-resolution slow-motion videos using standard cameras through frame interpolation. Essentially, they all take a high-resolution, low-frame-rate video at, for example, 30 fps and reconstruct a video with higher frame rate by synthesizing the missing frames in between, in this case increasing the frame rate to 60 fps. However, the main assumption in most of these methods is that the object motion between two frames is linear. Therefore, they generate artifacts for inputs with complex and large motion. To address this problem, in addition to the regular high-resolution low frame rate video, we also use a secondary high frame rate low resolution video. One provides spatial information while the other provides temporal information. The goal of our system is to combine these two video streams to generate a high-resolution slow-motion video. Our work has the following contributions: a 2-stage deep learning system that combines a hybrid video stream to generate high-resolution slow-motion videos, a flow estimation system that utilizes the hybrid video stream for alignment. We introduce an appearance estimator that utilizes the contextual and occlusion information to produce high-quality synthesized frames. To show practicality, we demonstrate our approach on 2 real dual camera setups. Let me reiterate our goal in more detail. In our dual camera system, the primary camera will capture the main video at high resolution and low frame rate. The secondary camera captures the auxiliary video at low resolution and high frame rate. Our goal is to combine these two video streams and reconstruct the missing frames and generate a high resolution, high frame rate video. Now, we will discuss the process for generating one of the output frames, but the process is similar for generating all the other intermediate frames. To reconstruct this frame, we use the neighboring main frames and all the intermediate auxiliary frames as input to our proposed slow motion video reconstruction system that generates the output frame. Our proposed system is mainly divided into 2 stages: alignment and appearance estimation. The alignment network warps the high resolution main keyframes to the intermediate frame. The appearance estimation then combines these frames to synthesize the final high resolution intermediate frame. Now I'm going to discuss our alignment process. During alignment, our goal is to estimate the missing frame by warping the left and right frames. However, unlike existing view synthesis methods that only use main video frames, we would also like to utilize the auxiliary frames to estimate the motion more accurately. To effectively utilize the information in both auxiliary and main frames, we propose to break down this process into 2 blocks: initial flow estimation and flow enhancement. The initial flow estimate only uses low resolution auxiliary video to estimate the low resolution but temporally accurate flows. The flow enhancement network then adds details to these flows by utilizing the high resolution main keyframes. First, I'm going to discuss the initial flow estimation component. The goal of initial flow estimation is to calculate the flow between the missing frame T and the left and right keyframes by only using the auxiliary videos. The output flow should match the dimensions of the high resolution main video frames. Therefore, we first bilinearly upsample the auxiliary video and compute the flows between the intermediate frame T and the left and right corner frames. To compute the flow between frame T and the left keyframe, we first estimate the flow between frame T and T-1, then T-1 and T-2, and so on until we reach the left corner frame. We then chain these flows to obtain the flow between frame T and the left frame. We can similarly compute the right flow. By computing the flow in this way, we can better utilize the information of all the intermediate auxiliary frames. We compute all the flows in this stage using a pre-trained flow estimation network, PWCnet. The estimated initial flows can be used to warp the left and right keyframes and produce a set of warped keyframes. Since the auxiliary video have a high frame rate, thus providing temporal information, the estimated flows are also temporally accurate. However, they are typically inaccurate around the object boundaries since auxiliary videos have low spatial resolution. Therefore, as shown here, the warped images using initial flows contains artifacts around the motion boundaries. To fix these artifacts, we enhance these flows using the high resolution keyframes in the next step. We are done with the initial flow estimation. Now I'm going to discuss our flow enhancement component. To enhance the initial flow estimate, we use the auxiliary target frame, keyframes, the warped keyframes, and initial flows as input to our flow enhancement CNN. The CNN then estimates a set of residual flows which are then added to the initial flows to produce the enhanced flows. This network basically detects the regions where the warped keyframe contains artifacts and uses the high resolution keyframes to improve the initial flows in these areas. In addition to the residual flows, the flow enhancement network also estimates a set of visibility maps which helps with occlusion handling. We will show the effect of these maps later. We have now warped the keyframes during alignment. Next, we will take a look at the appearance estimation stage. The goal of the appearance estimation network is to combine the registered warp keyframes along with the auxiliary target frame to synthesize the final output. This network, however, is not able to produce satisfactory results, especially in regions with motion. Here, I'm showing an example result produced by this network, and as you can see, it contains ghosting artifacts on the moving areas. To explain the reasons for these artifacts, I'm going to show you the inputs to this network, specifically the left and right warped keyframes. As you can see, the left warped keyframe contains artifacts on the ball and juggler's arm, since these areas are not visible in the left keyframe. On the other hand, these areas are artifact-free in the right warped keyframe. Unfortunately, the appearance estimation network is unable to discard the regions with artifacts from the left keyframe, producing results with ghosting artifacts. To resolve this issue, we guide the network to use the correct information from each frame through visibility maps. As you can see, in the areas where the left warped keyframe contains artifacts, the visibility maps has small values. On the other hand, these regions have large values in the right keyframe. Note that these visibility maps are estimated using the flow enhancement network during the alignment process. By incorporating the visibility information, the appearance estimation network is able to avoid the ghosting artifacts and produce a high quality result. Here, I toggle back and forth to show the difference between the results with and without visibility map. To incorporate the visibility information, we simply multiply the visibility maps with the warped keyframes. Now, this network produces reasonable results in most cases, but struggles around the motion boundaries. Therefore, we also add contextual information by processing the keyframes using a ResNet 18 network. This example shows the effect of contextual information. The network is able to suppress the artifacts on the rider's moving leg by utilizing the contextual information. We have discussed both the stages of the network. Next, I'll discuss our dataset. To train our system, we need high-resolution low frame rate main video, low-resolution high frame rate auxiliary video, and the corresponding high-resolution high frame rate ground truth frames. We generate our dataset synthetically from a set of high-resolution 240 fps videos. The auxiliary video is generated by downsampling the high-resolution video. We take every 7th frame from the original video to obtain the main video. The 7 intermediate frames act as ground truth during training. Now, we take a look at our results and compare them with the existing state-of-the-art methods. We compare our approach against temporal upsampling methods, super slow-mo and Dane, which interpolate missing frames between the main video frames. We also compare against spatial upsampling methods, EDVR and DUF, which generate high-resolution videos from low-resolution auxiliary frames. This is a synthetic example where the main video is sampled from a 240 fps high-resolution video. The auxiliary video is obtained by downsampling the original 240 fps video. The video super resolution method, DUF, produces unnatural looking output video. Similarly, EDVR is unable to reproduce the details by only using auxiliary frames. Super slow-mo, the video interpolation method, is unable to generate a coherent video due to large object motion. Dane similarly produces ghosting artifacts. Our approach generates a high-quality result with minimal artifacts. For comparison, here is the ground truth. To demonstrate the practicality of our approach, we construct two dual camera rigs. A smartphone camera rig contains two smartphones for capturing the main and auxiliary videos. We also built a digital camera rig with two cameras separated by a beam splitter to emulate a small baseline setup. We first look at an example captured using the smartphone camera rig. This is an example with input containing motion blur and large motion. The motion blur is less pronounced in the auxiliary video. The video super resolution method produces a blurry result. Video interpolation result, on the other hand, has severe artifacts caused by large object motion. Our approach generates a good result despite motion blur. Next, an example from the digital camera rig. This scene shows a rotating basketball. The auxiliary video is captured at a very high frame rate. EDVR is unable to reconstruct the details on the basketball using the auxiliary video. Dane produces results with artifacts caused by temporal aliasing. Our approach correctly handles the motion and reconstructs the detail on the basketball. In conclusion, we proposed a two-stage learning system for combining the two input video streams and producing high-resolution slow-motion videos. We did this through a flow estimation system that effectively utilizes both input videos as well as an occlusion and context-aware appearance estimation network. We showed practicality by demonstrating results on two low-cost 12 cameras. Our results showed significant improvement over existing methods. Here are the acknowledgements. Thank you, and I'd be happy to take any questions.
Thank you, Avinash, for the talk and the very nice results in your presentation. I'll start off with a few questions of mine, and then I'll move on to the live chat questions. So one small detailed question is, how did you attain ground truth for the visibility maps?
So we didn't have any ground truth optical flows and visibility maps. We first only trained the optical flow network. So during optical flow training, we had an equation in which the network had to produce visibility maps in a way so that it generates output closer to the ground truth. So we had a loss function which penalizes the network and forces it to produce good quality visibility maps, which can be used by the next network.
Okay, yeah, thank you. So there's a question by Hajime Nagahara, and also mixed with my question is, does the disparity of the two cameras affect the result when the target object is close to the camera?
Yes, so when the target object is very close to the camera, we observe that the auxiliary video and the main video the object appears to have a large disparity. So this causes a problem, and the output video has artifacts. We have added a result in our supplementary video as well as the paper, which shows the effect of large disparities. And this is because our network has been trained to account for a small disparity. So if you have slight misalignment, so since this approach is mainly focused on cameras with small baseline, so we try to train our network to be robust to small misalignments. So for small disparities, our network is able to produce good results. But if we have very large disparities, then yes, our network produces results with artifacts.
Okay. Thanks. So there was another question by Jingwei Gu, and I think kind of connected with a question by Mel White is, an alternative approach is to do super resolution for low-res videos with high-res keyframe as guidance. How does this method compare with flow-based method?
So we in our paper in the initial stages, we also show an approach in which we pass the main keyframes along with the low resolution frame and try to get an output with super resolution. But in that case, the network is not able to align the images, so it's not able to find the objects and in the low resolution and find its corresponding objects in the high resolution frames, since first of all, we are processing on 1080p videos. We are processing the 1080p videos, so the motion is very large, and so it's difficult for the network to trace the objects in the keyframes, high resolution keyframes, and the low resolution frames. So it's not able to align those objects. So in static regions, the result is very good. But if you have a moving car, the details are blurred out. We have a result in our paper showing this effect.
Okay. And a question from Suren Jaisurya is, has any indoor scenes with flickering light been tested?
We have not tested any scenes with flickering light, but we do have an example in low lighting conditions in which we also have a sort of flickering light, but not a large source of light. So in that case, we also observe the rolling shutter effect, where since it's due to the rolling shutter effect, the reflection of the light is observed in the one frame, but the light is off. And in the next frame, the light as well as the reflection is visible. So in the normal video interpolation methods, it seems like you can see the reflection of the light first in slow motion, and then the light is turning on. But our method is able to get the information from the low resolution frames and see that the light was on, and is able to therefore generate correct outputs with light on from the beginning of the frame.
Okay. Thanks, Avinash. Thanks for the questions and the presentation. Please continue to ask questions on the live chat, and Avinash or the authors would be able to answer there. Just a quick note, the chat will be live even after the session ends for 4 to 5 minutes, so that all the authors have the chance to answer the questions. With that, we can actually move on to the second paper of the session. The second paper of the session is per image super resolution for material BTFs. And the authors are Dennis Denbrock, Sebastian, Michael Weissman, and Reynard Clay. And with that, take it away, Dennis.
Modern display devices include large ultra-high resolution screens and highly immersive virtual reality appliances. They enable a very true-to-life user experience. When it comes to realism, measured material appearance plays an important role. It is often represented in the form of bidirectional texture functions, or BTFs for short, which may be considered an image-based variant of SVBRDFs, consisting of thousands of textures which are interpolated to obtain reflectance data for the desired combinations of angles of incoming and outgoing light. BTFs are typically obtained using highly specialized acquisition devices featuring a multitude of light sources and cameras. As such, they experience leaps in resolution less frequently than the commonplace display devices. Moreover, they always represent a trade-off between texture space resolution and maximum sample size. If a BTF's texture space resolution is too low with respect to the device it is displayed on, The user may experience a blurry or pixelated material, particularly in close-up views and broken immersion. Texture space BTF super resolution is thus a desirable asset. While there is an abundance of single-image super resolution algorithms, both classical and, most recently, based on deep learning technology, and also extensive work on multi-view super resolution for diffuse materials, SVBRDFs and BTFs have seen much less attention. The only work we are aware of is due to Dong et al. Their method is based on classical single-image super resolution applied to compressed BTFs for robustness and runtime enhancements. In our work, we take things one step further and apply single-image super resolution based on convolutional neural networks to BTFs per measured image. Our goal is not to find the very best possible network architecture for this task, which we consider a technical detail, but rather to investigate whether the given approach is feasible in the first place. This is not clear a priori, as it comes with a number of open questions concerning high dynamic range, scale invariance, and consistency in the angular domain. In BTF image data, highlights and shadows often appear in a single image, widening its dynamic range to well above the usual 8-bit. As far as we are aware, the applicability of super resolution to HDR data has not been investigated yet. Consequently, no pre-trained networks are available. Moreover, acquisition devices usually measure on a fixed scale. Therefore, the only high-resolution ground truth available for training is the actual measured data. It is not clear whether this is sufficient for upsampling device resolution data. Finally, it remains to be seen whether upsampled BTFs behave plausibly in the angular domain. To illustrate, consider the image on the right, upsampled after tone mapping using a pre-trained state-of-the-art network. While the image is very sharp, the network apparently hallucinates quite a bit, and the result does not resemble the actual material very closely. It is unlikely for the hallucination artifacts to be consistent image by image. Instead, we would expect flickering to occur in animations. For this reason, we chose a relatively simple network architecture based on the work of Shi et al. It is a convolutional network which takes a low-resolution input and successively computes a number of feature maps, which are then combined to the high-resolution output in a subpixel convolutional layer. Additionally, we introduced a skip connection, feeding the first layer's output to the penultimate layer, along with batch normalization, which enhanced the result significantly. There are a number of possible choices for input data. One could simply consider the entire BTF as a very high-dimensional image, or use eigentextures from a compressed representation based on matrix factorization, either as a whole or image by image. Another possible choice are the rectified and resampled images, that is, the BTF's textures, image by image. Empirically, we found the color-corrected HDR combined measured images on an image-by-image basis to yield by far the best results. We suspect that entire or compressed BTFs are too high-dimensional, and that eigentextures image by image vary too greatly in the frequency domain to give meaningful results. Conversely, rectification and resampling produce extremely low-frequency images for grazing views, which are the majority, which may cause unsuitable kernels as well. For training and testing, we use our database of 24 BTF measurements, 12 of which are leathers and 12 of which are fabrics. From each class, we randomly pick 2 materials for testing and 1 for validation in the training step. Each BTF measurement consists of about 26,000 images, cropped to a region of interest of 200 by 200 pixels. In order to answer the question of scale invariance as well, we set our experiment up as follows. Our network receives as input images downsampled twice by a factor of 2, and the corresponding images downsampled once as output. For evaluation, we use the resulting model to upsample images downsampled to 100 by 100 pixels to our ground truth resolution of 200 by 200 pixels. From the result, we produce actual BTFs by rectification and resampling. We train the network using a random subset of 5% of the original images in order to keep resource consumption acceptable. We have not found this to compromise quality and did not expect so because of the high degree of redundancy of BTF data. As usual, we train on patches, in our case of size 17 by 17 following Shi et al. Also following Shi et al., we use 4 hidden layers with feature maps of dimensions 64, 32, 32, and 4, and kernels of sizes 5, 3, 3, and 3 respectively. We observed the algorithm converge after approximately 100 epochs. Due to the 5% subsampling, we were able to keep the entire database of training patches in our off-the-shelf workstation's RAM. The training step thus took only about an hour. In testing, we upsampled our testing materials measured images from 100 by 100 to 200 by 200 pixels. By rectification and resampling, we obtained BTFs with a texture size of 128 by 128 pixels. This step took approximately 30 minutes, most of which were spent in the resampling step. The algorithm by Dong et al. Took about 15 minutes because resampling occurs before upsampling there. It is possible to improve our algorithm's runtime by means of sparse recovery. However, this comes with a trade-off between runtime and reconstruction quality. As we do not believe our runtimes to be prohibitive in practice, we did not investigate this in detail. The results on this slide show textures extracted from the BTFs obtained using the method proposed by Dong et al. And ours, along with the corresponding ground truth. Clearly, our results are more faithful to the ground truth than the state of the art. The images are sharper overall, and highlights are preserved better. On this slide, we present renderings of a selected testing material for the ground truth, the method proposed by Dong et al. And ours, and a standard scene featuring environmental lighting. Again, our results are noticeably sharper than the state of the arts. We find this particularly obvious in the 3D model's bottom region. We conclude that at least for moderately glossy materials, the high dynamic range does not pose a serious problem. Moreover, the model appears to be reasonably scale invariant. Recall, it was trained on data downsampled twice. We verified scale invariance further through an additional experiment we explain in the paper. It remains the question of consistency in the angular domain. While no artifacts are visible in the static rendering, this property is easiest to assess in animations. The following short clips show renderings of the ground truth on the left, of our results in the center, and 2 times the difference image on the right. Again, our results resemble the ground truth closely, and no flickering occurs. Our goal was to investigate the feasibility of deep learning-based single-image super-resolution in the context of BTF super-resolution. Considering our results, we believe that it is indeed feasible and likely suitable for practical use. In particular, our network deals with high dynamic range data, can be trained on data which is realistically available, and produces results which are consistent in the angular domain, preventing flickering in animated renderings. We expect more sophisticated networks to possibly give better results, perhaps even higher upsampling factors. However, care has to be taken that the resulting BTFs are still plausible in the angular domain. Another interesting question is whether the network can be tailored more specifically towards BTFs, for instance by taking multiple views into account. A possible means to attack this problem may be BTF models of very low dimension, such as the neural BTF compression proposed by Reiner et al.
Thanks, Dennis. Thanks for the awesome talk and also very good results. Let me start with my own questions. So one of the questions I have is, can a physics-based model be used to improve anything? Do you think there is a space for physics-based model to be incorporated?
Certainly, yeah, you could principally do something like implement rendering loss, for instance, I guess. We were experimenting in that direction, but this is computationally very expensive, and so far we haven't been able to achieve any results with that approach. But it seems promising. We just have to figure out how to make it reasonably fast.
Okay, thanks. So you had explored like a low computational neural network. Does it give you the benefit of fast rendering? Is it do you get the benefit of fast rendering of or the creation of high resolution BTFs?
I'm not quite sure I understand the question. I mean,
I can repeat. So
no, I mean, what exactly do you mean?
So you have a network to reconstruct the high resolution BTFs.
Exactly. Yeah.
I'm just asking about like how quick it is and can it do real-time rendering of high resolution?
Ah, okay. No, it can't. Yeah. So the evaluation is pretty fast, but initially we were hoping that we could also use our algorithm for the purpose of compression and doing rendering such that we could fit 4 times larger BTFs on a GPU, for instance. But unfortunately, it's too expensive. Doesn't work that way, even after pruning the network.
Okay. So just give a minute. And what other things do you think is the future work? And like, do you think improving high resolution plus something else is a question that needs to be answered?
I mean, of course, super resolution, in particular for material appearance, is or any kind of super resolution is a very, very wide field, and there are lots of possible approaches. For instance, I mean, we have a talk about light fields in this session, I think, and approaches like that, for instance, also apply in principle. Although previous work in that area is, I think, sufficiently different from what would be necessary for the case of BTFs, that it is safe to say that nobody has explored this really yet, and this is something that could be done. Although I personally envision that it would be most interesting to come up with some kind of optimization problem where one would solve directly for a compressed representation of the BTF. Probably using physical modeling as you proposed.
One last question from Akshat Dave. How robust is the approach as the glossiness of the material is varied from diffuse to shiny?
Yeah, on the database that we have on our disposal, it was very robust. So for all the materials we have, it worked. But we didn't test this on materials which are very glossy. And because this kind of materials is typically not the ones you would model using BTFs because of the relatively low angular resolution. So you would probably use SABRDFs for that kind of material. But this is also a direction for future research, I guess, doing this on high resolution SVBDFs.
Thank you, Dennis. Thanks for the presentation and the answers. Right now, we can move on to the next paper, and do ask questions of the paper that is live during the live video on the comment chat, so that I can ask questions after the video. So the next paper is high resolution light field recovery with Fourier disparity layer completion, demosaicing, and super resolution. The authors are Mikhail Lependu and Aljosa Smolik. Please take it away, Mikhail.
Hello, it's Mikhail Lependu from Trinity College Dublin. I work in the vScience team led by Alyosha Smolich, who's my co-author. So the paper I will present covers many techniques related to the capture of high-resolution light fields using a representation of the light field called Fourier disparity layers. So I'll begin this talk with a few words on the motivation of this work and also a quick introduction on the Fourier disparity layers, or FDL, which we introduced in a previous work. So then I can present the main contribution of this paper, which consists in using the FDL model for high-resolution light field recovery. So that includes mainly super resolution, completion, and color demosaicing. And finally, I'll show the results of our experiments that combines these applications in a practical scenario with light field cameras. So in this talk, I will consider 4D light fields, which can be seen as 2D arrays of 2D views of the scene, and where each view is an image with two spatial dimensions, x and y, and the viewpoint can vary along a plane. That forms two other dimensions, uv, called angular dimensions. So a very common problem that arises in the capture of light fields is the trade-off between spatial and angular resolution. For instance, a very intuitive way of capturing a light field is to use a camera array where each camera can capture a high spatial view with high spatial resolution, but then we obtain a low angular resolution because of the space between the cameras. On the other hand, we can use a lenslet camera to have a very high angular resolution with very dense viewpoints. So it looks like a regular camera, except that it contains an array of microlenses in front of the sensor to split the light rays coming from different angles. But the problem is that the spatial resolution now depends on the number of microlenses rather than the number of pixels. So we obtain a low spatial resolution with spatial aliasing, and there are also other difficulties such as depth-dependent blur, an irregular spatio-angular sampling because of slight misalignments between the microlenses and the sensor. Also, color demosaicing is more difficult to do because traditional 2D methods are not ideal for for the sensor that mixes spatial and angular information. So all these problems are interdependent. So instead of a step-by-step approach that accumulates errors at each step, we want to solve all these problems simultaneously. And for doing that, we propose an optimization framework based on the Fourier disparity layer model, the FDL model. So in this model, the scene is decomposed into a set of additive layers, where each layer is associated to one disparity value. And the layers are optimized in a way that any view of the light field is rendered simply by summing shifted versions of the layers, and where the shift, the translation vector applied to a layer, is equal to the view position uv multiplied by the layer's disparity value. So the reason it's called Fourier disparity layers is that the inverse problem that consists in constructing the layers from the light field views is very convenient to solve in the Fourier domain. So in a real light field like this one, in practice we would need around 20 layers, and we can use them for real-time rendering of any view position and with refocusing, and also with the control of the aperture size and shape. So now, to understand the layer construction optimization, let's have a look at the mathematical relationship between the views and the layers. First, in the pixel domain, each layer is translated by a vector, so we need to shift the spatial coordinates. But in the Fourier domain, this shift operation is directly expressed as a multiplication by a complex exponential for each frequency. So we have a linear relationship between the views and the layers that's expressed for each frequency independently of the other frequency components. So what that means is that now we can construct the layers by solving a simple linear least squares problem at each frequency component. And that's very convenient for parallel processing, for instance, with a GPU. So that's all for the introduction to FDL. Now, we want to use that model for applications such as super resolution, completion, or color demosaicing, but the previous layer construction method does not apply here because there are missing pixels in the views, in the input views, in these applications, so we can't compute their Fourier transforms. So we need to derive new layer construction methods that can ignore the contribution of the unknown pixels, and this way the layers will naturally combine the known information from the different views, and then we will only have to render the FDL to reconstruct the completed light field. So let's start with the case of super resolution. Here we don't know the full high resolution views, but we know the masked views with all the intermediate pixels set to 0. So in the pixel domain, the masking operation is just a pixel-wise multiplication with a sampling mask equal to 0 at these intermediate positions. But in the Fourier domain, it becomes a convolution with the Fourier transform of the mask. So what are the effects of this convolution on the relationship between the layers that we're looking for and the masked views that we know? Well, first it remains linear because the convolution is a linear operation, but now the convolution introduces dependencies between frequencies. So we can't process each frequency separately anymore, and actually the problem could become very large and impractical to solve with a linear least squares solver. But fortunately, in the case of super resolution, the mask is very, very sparse in the Fourier domain. Actually, the number of non-zero coefficients is equal to s squared, where s is the super resolution factor. So for 2 times super resolution, we would have only 4 non-zero coefficients. And because of that, there are only dependencies between frequency components that are in the same small group of frequencies, and the problem remains independent between different groups. So we can still solve it very efficiently with linear least squares. So in practice, the input views are also are not only degraded with low resolution sampling, but also with blur. So to deblur the images in the super resolution process, we must include a filter that models the blur of the view, and in the Fourier domain, it's just a weight applied to each frequency. And that also works with depth-dependent blur because we can use different filters for each layer. For light field completion, the problem is similar to super resolution, but this time the sampling mask has no reason to be sparse in the Fourier domain. So we can't simplify the problem, and then we use a different approach with an iterative algorithm. So we first initialize the pixels, the unknown pixels, and then iteratively we construct the FDL from the current views and reconstruct the views from the FDL, which has the effect of filtering the inconsistencies between the views. Actually, here we can use the FDL construction with the super resolution if we want to do completion and super resolution jointly. And the next step is to reset the non-pixels to their original values. This way, the unknown pixels are only the unknown pixels are filtered, and iterating that way progressively removes the initial contributions of the unknown pixels. So the demosaicing problem now, so again, is similar to super resolution or completion, but this time with a different mask for each color component. So instead of doing super resolution on each color component separately, we can exploit the correlations between the red, green, and blue signals. This way, for a pixel with one known color component, it will help recover the other components more accurately. So the assumption we make here is that the red, green, and blue images should have similar intensity variations spatially. And we enforce this prior in the FDL construction with a regularization term in the optimization to minimize the differences between the Laplacian filtered red, green, and blue images. And that's an example of demosaicing result either with color regularization in the middle or without on the left. And we see that the regularization removes the color artifacts that are visible on the left column. Now, we want to test everything in real conditions, so we have made experiments with light fields captured using a Litro Illum Landsat camera. So first, from the raw sensor data, we had to rearrange the pixels to form the low resolution views. And even in this low resolution format, the views are incomplete. And so that's because of two things. First, there's the Bayer color filter array on the sensor for RGB capture. And secondly, there is an irregular spatioangular sampling because of the imperfections in the alignment between the Landsat array and the sensor. So given these views with their masks, we can construct the FDL using the completion method jointly with super resolution in demosaicing. And we can finally render the high resolution images from the FDL model. So our result is on the right side, and on the left-hand side is the conventional light field extraction pipeline that uses a step-by-step approach. And on top of it, we applied a recent deep learning-based light field super resolution called Deep LFSSR that we choose because it was among the best, along with our method, on another benchmark that we did to evaluate the super resolution separately from the rest. Yeah, but in this application, the views extracted with the sequential pipeline already have resampling and demosaicing artifacts, which are then amplified by super resolution. So we actually obtain much finer details with our method by doing everything in one optimization jointly. And the improvement is also very visible in the background, thanks to the depth dependent deblurring that we do, and which can't be done in most super resolution methods. Now, the official Lytro camera software does better than the conventional pipeline, but with our method, we can still recover finer details and also a larger depth of field. And we don't have depth map related artifacts because we don't use depth maps. Okay, so to summarize this work, it adds up to the FDL light field processing framework, both with new theoretical developments about optimization and resampling in the Fourier domain, and with various applications, including super resolution with depth-dependent deblurring, completion, and color demosaicing. Also, two important aspects of the approach are that everything can be performed jointly for optimal results in real conditions, and it does not require depth maps because we only use a single disparity value per layer. Yeah, also, I want to mention that the code is available on GitHub. So thank you for listening, and I'm looking forward to chatting with you and having your questions and feedback. Yeah, see you soon.
Thank you, Mikhail. Thank you for the nice presentation and very good results. I'll ask questions. So first question, one question from me is, how do you handle imperfections in the light field camera, like misalignments and aberrations?
Well, in the light field cameras, there's, I don't know what you mean exactly by misalignments, but there's views are not exactly, cannot be considered as exactly in a perfectly regular grid. Mm-hmm. But there's in the FDL process, there's a first calibration step that can be done to find exactly the optimal positions of the views, as well as a list of disparity values to attribute to each layer. So this this calibration step does that.
Okay, thank you. And some questions from the chat. Vishwanath Saragadam asked the question, does splitting into layers account for possible occlusions at layer boundaries?
So there's no exactly layer boundaries because it's additive layers. They are summed together. In the case of occlusions, there might be some errors if it's large occlusions. In practice, it can, like when there are large occlusions, they kind of become a bit transparent. Like the occluder appears a bit transparent, but it's not too visible for the kind of light fields that are captured with a Lytro camera, which have more limited angular resolution, I mean depth of field, and also. There's sorry, I forgot what I was about to say. Anyway, yeah, it's not a too big problem for this kind of light fields.
Okay, I'm commenting two questions from the chat, which is similar. So, would the proposed method be able to do view extrapolation and interpolation?
Yes, so it's actually that was the object of the previous paper that was published on the FDL. So that was one of the applications: view interpolation, extrapolation as well, but in a more limited way. We can't go too far. At some point, it gets the results get quite bad. But yeah, technically it could. Yeah.
Okay. One last question. How does this method perform when you have a continuously varying depth, for example, a slanted ramp?
Well, it works with more layers. So in practice, with the if we have enough layers, it works well for this kind of cases because again, it's additive layers, and there's all the optimization that that makes the transition smooth. It's not like having separating the layers with some alphametric and a depth estimation. So there's no discontinuity. So there's no real problem for that.
Okay. Thank you, Mikkel. Thanks for the answers.
Thank you.
And with that, we'll move to the next paper, the last paper of this session. This paper is called One-Bit Time-Resolved Imaging. This paper was accepted to the PAMI special issue, as well as this paper also won the Best ICCP Paper Award. The authors are Ayush Bandari, Miguel Heredia, and Otmar Lofeld. And we'll go on with the video. Take it away, Ayush.
Welcome to our talk on one-bit time-resolved imaging. The key takeaway of this work is that we are able to recover time-resolved information, for example a 3D point cloud of a scene, from a sequence of ±1 symbols. Capturing the plane-optic function is the holy grail in imaging. In order to capture the high-dimensional plane-optic function, ideas such as illumination diversity and view diversity have been used in the literature. That said, in all such methods, the temporal information was discarded. If we consider the speed of light to be finite, then the information in the time delays or the echoes of light, encoding the scene parameters at different time scales, can be harnessed in unconventional ways. Time-resolved imaging systems are active systems, and light backscattered from the active illumination is recorded at each pixel as a temporal profile. This leads to larger volumes of recorded data. In the context of time-resolved imaging, in 2012, Andreas Welten, Ramesh Raskar and colleagues showed the first prototype that was capable of imaging non-line-of-sight scenes. Since then, time-resolved imaging has become a very active area of research and several new advancements have been made. Current hardware that facilitates time-resolved imaging can be broadly categorized into lock-in sensors, SPAD, and streak tube-based solutions. These different hardware solutions offer a trade-off between temporal resolution and spatial resolution. With streak tubes, it is possible to have a temporal resolution of the range of picoseconds. However, you can only scan one line at a time. On the other hand, lock-in sensors are more flexible as they have a wider spatial resolution, up to 160 by 120 pixel array, and hence this is best suited for consumer-grade applications. Despite the time-resolved imaging hardware advances in the last many years, we still do not have a sensor which matches the spatial resolution of a conventional digital imaging sensor. This is because each pixel of a time-resolved imaging sensor is equipped with an analog-to-digital converter which samples temporal information. Hence, as the spatial dimension increases, so does the complexity of the measurements. To overcome this barrier, we propose a one-bit sampling architecture which massively reduces the complexity of analog-to-digital conversion. In the terms of hardware technology integration, as we have shown in this paper, our one-bit strategy is a natural progression to the evolving time-resolved imaging hardware. To this end, our approach relies on the sigma-delta modulation scheme, which is a very mature analog-to-digital conversion technology. Here are some key features of our approach. We use a one-bit sampler for measuring the time-resolved information at each pixel. Thereon, our algorithm takes the one-bit sequence as an input and turns it into time-resolved information. The upshot of our approach is that our low-complexity time-resolved imaging approach can potentially lead the pathway to megapixel-sized 3D imaging sensors. Here's a one-slide summary of our approach. In the leftmost figure, you see a 3D stack of conventional 16-bit PMD data, next to which we plot the corresponding 1-bit data in 3D. For a given pixel, we also plot the time profiles for both the conventional raw data as well as 1-bit data. As can be seen from our recovery at strategy, we can recover the time-resolved information as well as the raw data from 1-bit measurements only. To explain our 1-bit sensing strategy, we first revisit the time-resolved imaging pipeline. All time-resolved imaging systems comprise of active illumination, which is denoted by a pulse or wave P. We call it the probing function. This emitted signal interacts with the scene H and results in reflected signal R. The reflected signal then enters the time-resolved imaging system's electro-optical pipeline, and the result is the measured signal M. Finally, digital samples of the measurements are stored as temporal information per pixel. In the time-resolved imaging pipeline, the key bottleneck is in the very last step where digitization of information happens. If we replace the conventional analog to digital converter with a 1-bit analog to digital converter, the complexity of the system falls off tremendously. While in conventional systems, point-wise measurements of the waveform are obtained, which is following the principle of Nyquist and Shannon, in our approach, we follow a 1-bit mapping of the function f to the variable q with the help of the recursive equations which implement a signum function and an intermediate variable u. And despite the nonlinear operations involved here, the reconstruction formula is the same as Nyquist-Shannon formula. And this works provided that there is certain level of oversampling involved in the acquisition system. To explain the mechanism behind 1-bit sensing strategy, we start with the definition of a first-order finite difference filter. Higher order finite difference filter of order L can be obtained from recursive convolution of the first order filter. It is well known that such a filter is a high pass filter. Based on the finite difference filter V, we can represent the 1-bit samples as the difference between f, which is the function of interest, and some filtered noise u. From the Fourier domain representation of 1-bit samples, we observe that the presence of high pass filter V forces the unwanted variable u into the high frequency parts of the spectrum. Hence, if the function f is smooth or low pass, it can be purely concentrated in the low frequency region of the spectrum, with minimal but non-zero contamination from the variable u. Since v is not an ideal filter, there will be some contamination from the undesired variable u into the function f. This brings us to the question of how large can this contamination or error be. To this end, we discuss the results from Daubéchies and Devore. The key takeaway from the 1-bit sampling bound is that the maximum reconstruction error depends on the oversampling factor and the reconstruction filter phi. Higher is the oversampling factor, the more concentrated is the low-pass function around the zeroth frequency, and hence the less it is contaminated by noise, which is good for us. And the reconstruction filter, the smoother it is, the better it is for our ability to reconstruct. Both of these quantities depend on the parameter L, which is the number of taps used in the high-pass filter V. Since the emitted pulses used in time-resolved imaging are smooth functions, they are typically well suited for the 1-bit imaging. As a demonstration, consider the time domain calibrated pulse in figure A and its corresponding 1-bit measurements in figure B. In figure C, we plot the Fourier transform of conventional and 1-bit measurements and observe that the low-pass spectrum keeps the information intact. In the case of multipath imaging, the scene response function corresponds to a k-sparse signal where the sparse components refer to the scene reflectivities and depth, and therefore the measurements comprise of overlapping pulse echoes where the pulse is a function of the probing or the emitted pulse. We can now substitute this definition of measurements in the 1-bit representation, and its implication is that the low-pass part of the 1-bit spectrum encodes the scene response function in terms of its Fourier transform, which is a sum of sinusoids. From the previous slide, we have seen that the scene response function is encoded in the low-pass part of the spectrum of 1-bit measurements. As shown in step 3, we can calibrate the 1-bit measurements corresponding to the pulse phi, which gives its Fourier transform. Thereon in step 4, we can deconvolve the effect of this pulse phi, and we are left with the Fourier transform of the k-sparse scene response function. To estimate the component of the sparse signal, we are left with the problem of sign fitting. This is also known as the spectral estimation problem. Further details are listed in the paper. On the right-hand panel, we list the algorithmic steps for recovery of the multipath components from 1-bit samples. For our experiments, we use 16-bit PMD raw data as our ground truth and convert it into 1-bit data. And we use the same number of samples, and hence we don't use any extra oversampling than what is conventionally available. For the case of single depth, the experimental setup is shown with the help of the schematic above. We use conventional 16-bit data for reconstruction of depth map and then compare it for the 1-bit reconstruction scheme. Clearly, the reconstruction scheme with second-order finite difference operation leads to a much superior reconstruction. Continuing on the previous example, here we plot the amplitude and depth map for conventional and 1-bit schemes. We observe that second-order difference-based 1-bit scheme leads to a superior reconstruction, and this is consistent with the maximum error bound that we have studied before. Here we consider the case of diffuse imaging, which consists of 2 light paths. The experimental setup is graphically shown above, and the reconstruction with conventional data is also shown in the top row. In the bottom figure, we show reconstruction based on 1-bit scheme. Once again, we observe that the amplitude map in the 2 cases is almost indistinguishable. Here we plot the time profiles for k equals 2 and 3 light paths. Our experiments show that reconstruction from 1-bit measurements is equivalent to having raw data. Furthermore, we do not need any extra oversampling than what is conventionally available. We also show that in Fourier domain, the low-pass frequencies end up being a sum of sinusoids. Here we discuss algorithmic advantages of our approach. In literature, multipath interference is typically modeled as a discrete sparsity prior. Corresponding recovery algorithms are based on sparse optimization, and algorithms include methods such as orthogonal matching pursuit and lasso. Such methods are iterative, are computationally intensive, and may not be able to super resolve. On the other hand, our method is based on continuous time sparsity, uses non-iterative approach, and is much faster than existing methods, and hence may be implemented in real time. In closing, we have presented a new framework for time-resolved imaging. Our imaging setup is based on low complexity 1-bit pixel architecture. Although our work exploits oversampling, but this is not beyond what is conventionally available. For instance, we have shown that we can recover information equivalent to a consumer-grade 16-bit sensor. Our work leads to a new class of inverse problems. Here we address the problem of multipath imaging. However, problems such as scattered imaging and non-line-of-sight imaging still need to be addressed. On the recovery front, new or more efficient techniques may benefit from the emerging methods in deep learning. Finally, we did not address the case of continuous wave imaging. However, such models are based on sinusoidal features, and continuous waves being low-pass signals very much fall under the framework of our work. Thank you for your attention, and please do not hesitate to contact the authors should there be any questions.
Thank you, Ayush. Thank you for the amazing presentation and a very, very interesting work. You've taken up fundamentals of signal processing, computational imaging, and random processes to create this amazing work. And also, congrats for the award.
Thank you.
So I'll start with a question of my own question, and then I'll move on to the chat. Question I have is there any advantage of using first-order finite difference over second-order finite difference?
Yes. So if you look at the hardware, in implementation, what is happening is that the order defines how many taps you will be using for the implementation of 1-bit scheme. So the smaller the number of taps for implementation, the simpler is the hardware. That said, I just want to insist on one point, that analyzing mathematical analysis of these schemes is extremely hard because it's a nonlinear. There's a nonlinear signum function sitting inside. So therefore, typically in literature, they implement one first order scheme. And the reason I show a second order scheme is just to show you that there's a jump in reconstruction error. And that is just to show that. But yes, if your question is 1-bit better or second, it really depends on your budget of where can you put, how many resources can you put.
Okay. Right. Thank you. That makes sense. Some questions from the chat. Vishwa asks, what is the minimum resolvable time gap between 2 pulses, and how is it related to the rate of sampling?
Right. So the way I go about this answer is that, as I mentioned, this scheme is based on a nonlinear operation. So answering that question is extremely hard because there are no tools to my knowledge that exist or have been published. That said, I recently did some analysis, and for me, what it looks like is resolvability will be a function of oversampling, because here there's even in the noiseless case. So if there's no noise, you can resolve exactly. There shouldn't be any problem. However, there's an element of noise that comes in because of this 1-bit coding. So now the question is, how much can you resolve will depend on that noise. And I think there's no clear answer to this question, but oversampling dramatically affects the resolution capacity. So so if I have to put my neck on the line, I would say 1 over square root factor improvement you will get in resolution. So you can close this gap as 1 over square root oversampling factor, but nothing more precise I can give as of now.
Okay. All right. Thank you. Another question from Byungju is, how does it work for an object with interreflection? For example, a concave object.
So I would say that this question has no relation with our work in particular. It's a general question for time-resolved imaging, with or without 1-bit. I think there's a couple of works which address this problem, and I think just the approach that we have mentioned here would not be suitable for that particular method, because as the information in interreflections increases, it's no longer a sparse sum of spikes. It becomes a continuous process, like a decaying exponential. So we would have to resort to a different method. I personally did not invest effort in that, but some other colleagues have worked in that area, and I think literature will be able to answer that question.
Thank you. Yeah. So Atul Ingle asked question that currently there are quanta image sensors that produce binary image frames at more than 10K frame rate. Does your theoretical framework apply there?
So my understanding of these quanta imaging sensors suggests that they are sampling spatially. We are sampling temporally, 1-bit. So our binary phenomena happens temporally, not spatially. Okay. So if my understanding of the quanta sensor is correct, I assume that they sample spatially 1-bit.
Yes.
So there you will get, even if you take one shot, you get a QR code looking image just because the entire sensor spatially is 1-bit. We are 1-bit in temporal dimension. So I think there's a difference in the approaches.
Okay. I think they do take multiple frames where each frame is a binary frame. So over multiple time, then you have each pixel to be varying in bit. But then we can talk about that after.
Yes, I think I would have to look at that. So,
okay, no problem. So another question from Akshat Dave is, how does the per pixel footprint, that is the area on the chip, of the ADC in 1-bit sensor compared to a typical SPAD sensor with TDCs?
So we have not performed that kind of integration of technology, so I would not have any, I could not answer that question. But wait for 6 months once the COVID things goes down and we can raise some money, I would be more than happy to answer that question.
Okay, awesome. Thank you, Ayush. Thank you for all the answers. We'll end the session with this. 2 quick notes. The live chat is going to be active for 4 to 5 minutes so that the authors can have a chance to answer the questions in the chat, as well as you can have a few more questions. I am going to copy these questions and place it in the chat of the final video when it gets published. With that, the session ends, and hope to see you in the keynote session that's going to happen at 12:30 p.m. Central Time. All right. Thank you.